So once again, welcome everyone. My name is Magnus Melander and I'm the moderator of this little tinyML talks. I'm a co-founder of the Deep Tech Hub Things in Stockholm. And I'm also part of the committee that tries to put together the Swedish part of tinyML. You're welcome for this one interesting speech. And today we're going to talk about CMSIS-NN Optimizations for Edge AI, together with two friends from Arm, Felix Johnny and Fredrik Knutsson.
Hi, everyone.
Hello, everyone.
And then we have to be specifically single out that we have some good sponsors with us who makes those talks possible. So we're grateful for them. And it's Arm, it's Deep Lite, Edge Impulse, Maxim Integrated, Quexo, Reality AI, and SynSense. So big thanks for them. I would like to pre-announce the next Tiny Talk as well. It happens in about a week and it's Mohammed Zubair. These nice guys, we are still lacking a woman here, are the guys in our committee in the newly started Swedish chapter of tinyML. So it's Ali Baladar, who is a senior researcher at RISE, the Swedish Research Institute, and an assistant professor. Johan Malm, AI engineer at Imagimob, one of the most sophisticated and advanced startups in the space of Edge AI in Sweden. It's myself and Åke Wernlind, who keeps the committee together. He's also representing Imagimob AI. The topic of today is CMSIS optimization for Edge AI and our good friends at Arm, Felix and Fredrik. And here you can read a little about Felix, who primarily is a maintainer of the Arm's open source CMSIS-NN library. Yeah, you can read the rest of yourself. And Fredrik, he is in the technical lead for the Arm team working at Ethos Q55 and Cortex-M integration into embedded routing. So with that, let's hand over to Felix and start the presentation. Take it away.
Great. Thanks a lot, Magnus. And welcome, everyone. And thanks for tuning in to tinyML Sweden's first meetup. I'm Felix, and together with Fredrik, we'll take you through a session of optimization on Edge AI with focus on CMSIS-NN. So this is the rough plan that we have for you today. We'll start off with a very short introduction to Edge AI and Cortex-M processors. And that'll be followed by preparing for how you go about with your task of preparing for optimizations. And then we'll get into the details of how we actually do the optimizations in CMSIS-NN. And after that, Fredrik will take over for a demo of CMSIS-NN, along with a few words about how you integrate it with TensorFlow Lite Micro. And as for questions, please keep them coming, and we'll take them during the section slides in between. Maybe not after the very first one, as it's a very small section, but we'll stop for questions during the rest. So I'll start the presentation by saying that I'll skip the slide, as Evgeny has given a very good introduction to Edge AI already. Now, why do we target Arm Cortex-M processors? We have more than 52 billion shipped units, and enabling those units with machine learning capability accelerates the deployment of machine learning on the edge devices. And Cortex-M processors are power efficient, which fit into the tinyML requirements. Now, you could ask, why didn't we have this 2 or 3 years back, and why are we talking about this today? And a main reason for that is the availability of new models with lower memory footprint and compute requirements. For example, if you take MobileNet V2 in its floating point glory, it takes a few megabytes and some hundreds of million max. If we run this on a Cortex-M4, which is used in the demo later on, it quite likely will take tens of seconds or even a few minutes. But then enter %detect model, which is based on MobileNet V2, and it uses int8 as the data type. Now, this would run in less than a second. And that is one of the improvements that makes this possible. Now, when I started in machine learning, it was hard for me to visualize how a processor perceives a neural network model. And this slide is for people like me out there. So you can just think of a neural network as multiple blocks, which are operated by the processor, one block at a time. And you provide an input to the model, and then you get an output, which the data traverses through the entire compute blocks. And the time taken is what we call as inference time. And that is something which is we in the tinyML community are quite fond of, inference time. Yeah. All right, so now about optimizing. Now, why is optimizing for neural networks important, and how do we go about it? If we have to pick two main reasons, I would say power and cycle constraints would top that list. Extending the battery life of edge devices by reducing awake time is something which can actually make your application a realistic option and be a very powerful tool. And then if you take cycle constraints, it enables us to deploy more complex models within the same inference time budget and also meet real-time latency constraints. Now, the question is, whose responsibility is optimization? And as the proverb goes, it takes a village to raise a child. I believe everyone has a role to play in optimization, even though you might not realize that you can actually make a difference here. And I've listed a few options here, few areas where optimization can be deployed. It starts with the hardware design and then goes on to the software environment settings and to model hyperparameter optimizations and also to library optimizations. Today, we will focus on library optimizations and model hyperparameter optimizations. So we've talked about CMSIS-NN. So what is CMSIS-NN? Cortex Microcontroller Software Interface Standard is a framework which is a collection of API definitions, libraries, utilities, and methods, which accelerate the development of microcontroller applications. And this is something which is provided with a Apache 2.0 license, which means that you can use it free of cost on your public projects or commercial projects. And CMSIS-NN is just a tiny part of that. And to use CMSIS-NN, it's not necessary that you include the other modules as well. And the way to use CMSIS-NN is through TensorFlow Lite for microcontrollers, which is again a topic which Fredrik will touch upon later during the demo. Now, if you remember the small blocks of compute that we discussed earlier, what CMSIS-NN does is CMSIS-NN produces functions which are optimized to which act on those individual blocks. So you can look at CMSIS-NN as a collection of optimized functions. Great. Now, with that in mind, let's check with Magnus to see if we have any questions that we would like to address right now. You're on mute, Magnus.
Yes, we have one question, but that's already responded by Fredrik. That's a great idea to have two speakers who help each other. So
good to know. Great.
Keep going.
All right. So now that we know that we would like to optimize, so let's see what the first step in this process looks like. That is preparing for library optimizations. So this is the setup for the data that I've used. I've used a ST Nucleo board, and which has a Cortex-M7, and I've used the person detect model. And yeah. So the first step is cycle measurements. So how do you go about cycle measurements, and how does that look like? So this is a snippet of the person detect model. And you can see I've just listed the first 4 layers of the blocks. What we do is we do a cycle measurement on after each of those blocks. So we reset the cycle counter, let the layer execute, and then we log the cycle count. And we do this for the entire network. And then what we do is we group the cycle measurements together. What that means is, you see on the left-hand side, you have 3 depthwise convolution layers and 1 convolution. So we group the cycles for the depthwise convolutions together and plot that in a graph. So how does that graph look like? So for this specific person detect model, more than 99.95% of the cycles are split between just 2 operators. That is convolution and depthwise convolution. So this is a very good indication or a starting point saying that we don't need to care about the other 3 operators just for this specific model. And we can just focus on convolution and depthwise convolution here. So with that in mind, it's also good to set a target for the optimization. And setting a goal tells you like how realistic your expectations are in terms of optimization. So, and also when you perform your optimizations, you can actually measure how good or bad your effort is. And that is why it's important to set a target for optimization. And to do this, we usually split our effort into 2 analysis. One is cycle bound analysis, and the other one is memory bound analysis. So we'll go through this in detail next. So let's take cycle bound analysis first. So what do we mean by cycle bound analysis? It's basically about the processor's capability and its actual utilization. Let's take the case of a multiply accumulate operation, which is very common in neural networks, and especially in convolution and depthwise convolution operations. So we use a term called speed of light or processor capability, which is basically the processor's capability to execute a certain instruction. And in this case, for a Cortex-M4 can perform a multiply accumulate operation in 1 cycle, whereas a Cortex-M7 can do 2 at a time in 1 cycle. And the latest Cortex-M55 can perform 8 multiply accumulate operations in 1 cycle. So now that is our theoretical starting point. With that in mind, we then look at the actual cycles that were consumed, and then we divide those 2 to get a number called as the processor utilization, which is something between 0 and 1. Now, let's look at how this has turned out for the person detect model that we used. So we begin with the chart which we showed earlier, showing convolution and depthwise convolution consuming most of the cycles. And now let's look at the multiply accumulate operations, which are part of those 2 operators. You can straight away see that there is something fishy going on for the depthwise convolution, because even though it just accounts for 13% of the MAC operations, it actually consumes almost 40% of the total cycles. And if we plot the processor utilization number, you'll see that it's a very low 1.7% and a 6.9% for convolution, with the convolution being almost 4 times as fast than the depthwise convolution. Now, it's a little bit of it's an alarmist slide, to be honest, as it is a very unfair representation because convolution and depthwise convolution do more than just max. You have your quantization parameters like the filter offsets or the input offsets. And then you have the requantization option, which is a very cycle intensive operation. But irrespective of all that, the takeaway here is that there is scope for improvement. And that is what we focus on. So that was the cycle bound analysis. Now let's move on to the memory bound analysis. So it's roughly what this is about the theoretical bandwidth of the system that you have in hand and the effective bandwidth and the effective bandwidth and how they relate to each other. And one thing to notice for neural network applications is that you usually have different memory blocks that are involved. And usually it is about reducing the effective bandwidth, but not always. And together with memory bound and cycle bound analysis, you get an idea, like optimization. And what we try to do is like we try to strike the balance between the two. And the idea being, you want to fetch enough data so that your processor is not stalled for data. And at the same time, like you don't want your processor to be waiting on data. That is generally the idea on which we try to do the optimizations. So those are the theoretical aspects behind it. And now we'll get into library optimizations, which is CMSIS-NN in this case, and like what are the steps that we do in the optimization process, and also a little bit on model hyperparameter optimizations. Are there any questions at this point, Magnus?
Yes, we have a couple. Can you brief how depth-wise convert 2D helps in this scenario?
How it helps in this scenario. So this one is in a person detect, you would see that like you have a lot of point convolutions followed by depth-wise convolution. And that is depth-wise separable operation, which is a very common building block in neural networks. And the reason why you usually use depth-wise convolution is it has less max when compared to convolution. On the other hand, you spend more cycles for performing one MAC. So it's a bit of a trade-off. So if you want to reduce your max, that is one way. And also, yeah.
There is another one as well. Can you speak about the sizes of the inputs to each layer?
Sizes of input to each layer, I think like we'll handle that in a later section on model hyperparameter optimization later at the end of the section. So we'll take it there. Cool. Right. Now, moving forward. So what I've tried to do here is I've taken the case of fully connected operator, which we haven't discussed so far. And I've shown how we apply optimization techniques on that operator instead. And the reason being, it stands as the principles that we use there is more or less the principles that we apply on the other operators as well, like be it the image to column method for convolution or depth-wise convolution as well. We start with the input. And in a fully connected operator, you have an array of input, so which is n bytes in this case. And the data is stored contiguous in memory, so which is great. And then to produce one output, you need n filter elements, which are stored contiguous in memory as well. And to get for the second output element, you need a new set of filter elements. Now the start of the second filter block begins at the end of the first one. So, and the order in which you perform your multiply accumulate operations is the order in which data is stored in memory. And that is a very big plus when it comes to speed of an operator. And so you have your ducks in a row, and that is basically what most optimization techniques try to do. Like you want your data in the same order in which you want to process them. And depth-wise convolution usually has a lower cycle count or higher cycle count because the data is not arranged in order. So first, we talked about cycle bound and memory bound aspect. Let's take the memory bound aspect and apply that to this use case. So the code loop looks something like this. You have an input to which you add a fixed offset, and then you have your filter elements to which you add a filter offset as well, and then you do a multiply accumulate operation on them. Now the common part here is the input data. So what we can do is we can unroll the loop. If we unroll the loop, what we have effectively done is we have reduced the number of input vector reads by half. Now, reducing memory reads and reusing is a very vital aspect of optimization. And that is how we reduce the effective bandwidth of your system. Now, again, you could ask, why don't I unroll? If unrolling is so good, so why don't I unroll it 4 times or 5 times? Well, there are limits to effective unrolling. And here we'll see what factors affect that. It primarily depends on the number of general purpose registers and the vector registers that your processor has. So let's take this example that we had before, where we have unrolled it. And let's apply it to a general Cortex-M processor, which has 13 general purpose registers. So what I've done here is I've assigned a theoretical register to all of the variables which are inside that loop. If you start with the addresses, you have 3 addresses in the inner loop. And let's say we assign registers R0 to R2 for that. And you need 3 values, which are read out from those addresses. So let's put in 3 more registers there. And 2 registers to hold the sum, and 2 for the offsets, and 1 for the loop count. And that leaves us with just 2 empty registers. Now, this looks like a reasonable split, so meaning, and what we essentially would like to do is we want to be at the edge of register spills. So that is usually the point at which loop unrolling stops being effective. And this is something which you'll have to try out. At times, it might be okay to just, if there is 1 register spill happening, it might still be okay in terms of performance. But it's always good to try to be on the edge of register spills and see what suits the performance better there. Now that we have done that experiment, we also need to check that if the compiler output matches the expectation, because at times that it might not be the case. And the block that you see on the top is an actual code snippet from CMSIS-NN, and with loop unrolling by twice. And if you look at the code below, that is the generated disassembly for that. And since we increment the pointers by 1, you can see that the pointers are incremented along with the load. And that is something which is very important for optimization as well. This is something which depthwise convolution usually doesn't have as well. So in those cases, you would usually have an additional instruction which does the increment of the pointers. That basically means more instructions in the core loop and more time. And on the multiply accumulate, you operate on 1 operand at a time, which is fine at this point. So with that in mind, we go into the next step, which is the cycle bound improvement. And in this case, we want to use SIMD instructions for the multiply accumulate, which is single instruction, multiple data. And this is this table that we saw earlier. And this is a code snippet on how it would look on a Cortex M4 or M7. So you see the smlad instruction, which is the SIMD equivalent for a Mac. So that instruction is capable of performing 2 Mac operations in 1 cycle. And that is where you use the processor's capability. And the same thing for a Cortex M55, which has a multi-vector extension. We can actually load 16 bytes of data in 1 instruction, and it performs 8 instructions, 8 Macs in 1 cycle. And finally, on outside of the cycle and memory bound aspects, there's always simplifications to the core loop that can be done. The core loop is something which we would like to be as simple as possible. And any instruction which can be moved out of that is a good optimization to be done. And that is what the final step usually is. So in summary, you have your memory access optimizations, and also you have your processor capability optimizations. But a very important point is keeping the code as simple as possible. So yeah, what I'm trying to say here is like, it doesn't always have to be fancy optimization techniques that you use. Keeping things as simple as possible at times can be the best optimization that you do. And to the final part of this session, or at least my part of the session, is model hyperparameter optimization. And this will also answer the question which Magnus had earlier. Now, when it comes to hyperparameter optimization, there are different techniques available, like quantization. It could be 8-bit or 4-bit, or even binary networks, or pruning of the weights. But one aspect which is usually not talked about enough, and which you would find very less documentation about, is the unaligned aspect. So if you take a convolution example here, which with a 3x3 filter, and how this looks like in memory is something like this. So you have 27 bytes of memory which are contiguous and which are contiguously stored. Now, what happens is that at the end of this one, when the second filter block starts, that would not start on aligned memory access, on an aligned boundary, meaning you would get a penalty for unaligned access. And that is something which can really be detrimental to your optimization efforts. So you could have the best processor utilization techniques, but at times you would lose just on the memory accesses. Now, for this example, this one, we're talking about 1 million MAC operations. Now, if we change the number of input channels from 3 to 4, it's like this. And this basically results in increasing the max by 33%. So you started with 1 million max, and now we're talking about close to 1.3 million max. But despite that, it resulted in a 21% reduction in cycles. And that is a significant number of cycles. So, and this is something which is applicable to other operators as well, like max pool, average pool, fully connected as well. So using a memory alignment aware shape is necessary to get the best out of your optimized library. So with that, we come to the end of the first session and on to Fredrik's part for the demo.
Thank you, Felix. I think you're on mute, Magnus.
I'm trying to give Felix a question.
Yes, please.
What is the YouTube library URL for past session recordings?
Sorry, for past recordings of tinyML talks, or?
I don't know. What is the YouTube library URL for past session recordings?
Right. So that is, I mean, like that should be, that will be posted on the, you can search for tinyML as channel in YouTube. That is one place. And also the end of the talk, I think the link would be posted in the meeting link as well. So yes, you can have a look at it right there.
Okay, great. So let's hand over. Thank you so much, Felix. Let's hand over to Fredrik. And
thank you.
We have to keep an eye on the clock.
Yes, I will try to speed up my slides so we can focus a little bit more on the demo itself. So thanks, Felix, for a great deep dive into the world of optimizations. Now I'm going to talk about how to deploy these optimized CMSIS-NN kernels in a real scenario. And for that, I'm using TensorFlow Lite for microcontroller. So most of you have heard about TensorFlow, which is an open source model training framework for machine learning, and TensorFlow Lite for microcontroller is the dedicated runtime for microcontrollers. It can run on bare metal system. There's no requirement on OS. There's no requirement on heap. It has a really low memory footprint of about 20 kilobytes, and then scalable depending on how much of the operators you need. It has a set of examples and demos available on the homepage. We're going to demo one of them, person detection, today. It has more than 50 or maybe approaching 60 operators supported as of today. So we can go to next slide. Okay, so how do we merge together CMSIS-NN and the optimized kernels and the runtime TensorFlow Lite for microcontrollers? It's quite simple. You basically use a build system as listed here in the TensorFlow Lite for microcontrollers build system. And if you look at the block diagram to the right, you will see how an application calls into the TensorFlow Lite for microcontrollers parser, or the library, which then dispatches the compute to either reference kernel or optimized kernels, depending on availability. And we can skip to the next slide right away. Okay, so there. So reference kernels are there for availability. There's no optimization. They are written in pure C, so they are portable, they are readable, they are have a big coverage. Then if you want some more horsepower in your computation, then you use CMSIS-NN. And if you want even more horsepower, like you have to have some kind of dedicated computational kernel, such as Ethos U55. One of my colleagues will host a talk about that later this year, so I won't go any more into details on that. Okay, next slide, thank you. So, optimize where it matters. What kernels do we optimize? Quantization is a very important concept. Like Felix was touched upon, using a 32-bit float wouldn't be very suitable for a microcontroller use case. It takes up a lot of memory and it takes up a lot of MIPS to do the computations. So an 8-bit data type is more suitable. And if we go down to the specifics, we are using a symmetric int8 per channel quantized data type. You can see the formula there, and you can find a reference for it in a later slide. Operators, what operators do we optimize? I think we've talked about it a couple of times, but it's worth an extra mention. There are the main compute, the main number of cycles happens only in a few handful of kernels. So as we can see from the pie charts to the right, which represent the percentual number of cycles per operator, we can see that there's a lot of blue, a lot of orange, and a lot of yellow there, which corresponds to cycles spent in convolutions, stepwise and normal, and fully connected. There's also some computation spent in maxpool. So those are the ones that we have focused our CMSIS-NN implementation and optimization effort on. And we can go back. We're always open to hear more about what you see in a live out in the world. If you see if you have a network that consumes a whole lot of cycles in an operator that is not optimized, please let us know, and we consider optimizing that one as well. And best way of doing that is just filing a ticket on our GitHub repository. Okay. And so I mentioned person detection demo earlier. That's the one we're gonna show today, and all the instruction, everything is available on the TensorFlow repository. So just have a look at the links that we post later on in the session. So the what it does is that it detects whether it's a person in a picture or not a person, and to do that, a model is used, and that model consumes around about 300 kilobytes of flash, which is mostly consists of weights and bias, about 100 kilobytes of SRAM, and it has 31 layers and around 7 million max. So that's the model or the network. The input to the model is 96 by 96 pixel monochrome grayscale image, and the output is a person score and a no person score. If the person score is higher than the no person score, we will detect it as a person. Okay, and the hardware for this demo will be an Arduino Nano 33 BLE Sense with an ArduCam to capture the images. This specific hardware is powered by Arm's Cortex-M4. So if you remember from earlier slides, M4 has the capability of doing DSP-like instructions. The board has 1 megabyte of flash, 256 kilobytes of SRAM, and it's clocked at 64 megahertz. It's equipped with a diode, which will show a green light if a person is detected and a red light if the person is not detected. Then I think maybe a blue light flicks by as well as the image is being captured. Okay.
All right, I'll stop the share now, Fredrik, and so you can take over.
Thank you. So to start with, I can say that the Arduino IDE has TensorFlow integrated into it. And that version of TensorFlow that is integrated into it has the CMSIS-NN optimized kernels baked in. So you get it for free there. So in order to demonstrate the performance aspect of this demo, I have generated a library without the CMSIS-NN kernel. So that this is what we're going to see now. So I'm just going to take the camera and let me know, Felix, if it's possible to see the, I got the fixture here made out of my son's Lego. Got the camera.
I can see it fine.
Great.
Or you stop moving.
Yeah, I'm going to try to get it in there. Okay.
It's a little bit, yeah, it's good now. It's good.
Okay. So you can see the diode is actually, see if the demo guys are with us, not so far. It's actually detecting a person here, but the most important thing about this is to see that how much time it takes between the blinks. So one good way to do this is to look at the serial monitor. I will share my screen here. Sure, I'm talking about. So Felix, do you see my screen here?
Yes, I can see your screen.
Right. So I'm just going to start the Arduino IDE. Okay, let's see, we got 9 minutes, so that's, I think we're good. So if I do tools and serial monitor here, turn off the auto scroll. And if we have a look, how is the font for you, Felix? Is it readable? How about
now? It's good. That's good.
Cool. Okay, first line, starting the capture of the image. Takes in the JPEG image and converts it into a grayscale 96 by 96 pixel. And after that, it's done, and then it starts the decoding. And after the decoding is done, you get a person score and a no person score. And more interesting for this, the purpose of this demo is the clock tick between the two events. It's, as you can see, about 6 seconds. So that's what we've got without the CMSIS-NN kernels. Now I'm gonna show you how this is done with the CMSIS kernel. So I'm just gonna use the pre-canned version of TensorFlow that comes with the Arduino ID. So I just click install here. Done. I open the person detection demo, and I open here. And then we just compile and flash. So this will take a couple of minutes. So I thought we could take a couple of questions in the meanwhile.
Yeah. Is it okay if I take the questions, Magnus?
Absolutely.
Yeah. So looking at the questions, like a common question seems to be about CMSIS-NN support for RNNs. And so what I would like to say there is CMSIS-NN supports operators. So to run RNNs, like you need a framework like TensorFlow Lite Micro. And as long as so when it comes to CMSIS-NN, like you just look at the operator. If the operator in an RNN, and if the operator that is in RNN is in CMSIS-NN, that is basically the question. So the support basically comes from the framework and not in CMSIS-NN. And if you would like any operators that you would like to optimize, just let us know. And that is something that we can handle. And there is a question. So given your example from 3 input channels to 4 input channels, we actually get 1 input channel for free. Yes, that is true. But it comes with a memory penalty. Do we see a staircase pattern regarding latency and number of input channels? I'm not sure what you mean by a staircase pattern, but when you increase from 3 channels to 4 channels, yes, the number of cycles is reduced, but at the same time, like it involves using more flash memory and also RAM usage. And this is another question. Is there a tool that can help? Is there a tool that can help in deciding operator size with respect to optimized memory alignment? This is in relation to the last slide on memory alignment. That is a very good point. And to be honest, I would really like a tool like that, but I don't think we have one right now. But that is something which I would feel that there is a need and a market for that.
Good. We're almost done flashing the Arduino with the firmware.
Right, yeah.
Or did you have another question, or should I?
No, just go ahead. I think it's 100%.
Cool. All right. So we're done with that. So now I'm gonna show you the camera again. Can you see it good?
Yeah.
Felix, you're on mute. Do you see the?
Oh, sorry. Yes, I see.
Perfect.
The flashing red.
Yes. So as you can see, it goes a lot faster. We can now try out the capabilities of this demo. And as you may be able to see from the camera, there's an elephant right there, and it's detecting it as red, so not a person, which is expected. So we can flip the page here. Here's definitely a person. Albert, a brilliant person. So as you can see, it starts flickering in green. But more importantly then, how are we on, we can kind of see that the processing is a lot faster. But just to get the number on it, we go back to the Arduino IDE. And I hope you can see it now. And
yeah.
we open the serial monitor. We look at the same print as before, and image is decoded, which means that inference will start, and it's completed about 0.7 seconds later. So that is to be compared about to the 6-second time it took without CMSIS. So that shows clearly how much you can gain with CMSIS-NN by just using the processor in a more efficient way. In this case, we see a speed of about 8 times the performance. And that's that pretty much wraps up the demo. We got a whole 2 minutes to spare. Do we have more questions, Felix, or did we have
yes.
A couple of more slides, perhaps?
Do we have time for a couple of questions, Magnus?
I'm not sure. We have 2 minutes. We have to wrap up, I think, but we'll respond to the questions afterwards.
All right, yeah. And let me put the slides back on.
Yeah, so thank you so much for those 2 presentations. It's great to see, and we appreciate that a lot. So again, we have great sponsors: Arm, Deep Light, Edge Impulse, Maxim Integrated, Quixo, Reality AI, and SynSense. So thank you so much for helping us. And here you have a little bit more information on each of the sponsors. I will not take you through them, but take a look, and you can find it in the video and in the presentation material afterwards. And here's our next again. And I would like to thank you now all for joining us today in this talk. It's our first show from Sweden, and I hope you appreciate our first effort. And thank you again, Fredrik and Felix, for your presentation. And I'm looking forward to the coming talks and to the summit. And I hope you do that as well. So thank you so much, and have a great continuation of the day or evening, wherever you live. Thank you and goodbye.